Yeah. Well, good
Salve.
morning, everybody. So my goal today is to finish chapter 6. And we have done all the hard work. We've set down the foundations, the knowledge, the understanding of it. So the next step is just to apply it, to practice applying it. And I think we've done a lot of applications here. So excuse me, I think it might go pretty smooth in 6.7. We'll practice it and you'll see how it goes. Now 6.8, um, well, I'll decide on 6.8 as we go. If we don't have time, I'm going to make it optional, but I think we can fit it in, and it's not super hard. So let's get started. Okay, so I have a lot of stuff I wrote on this. These are things that the green things are things that I really would like to teach, but we don't really have time. Um, Newton's law of cooling, that's a really cool thing from physics. And logistics models are a really cool thing from exponential growth. I normally wouldn't talk about logistics at all just because we don't have time. But because of the coronavirus, I'm going to talk about logistics models just for a moment. We've been studying exponential growth. And if you've been looking at the internet, you've been seeing these models of how COVID, the number of infections and the number of deaths has been going exponentially. Now, in real life, when we look at the number, let's say days, and the number of infected people, exponentials go to infinity. Now, can the number of infected people go to infinity? Well, no, there aren't infinity people. So what happens with with exponential growth is it turns into a different kind of model. There's a point in exponential growth where sometimes you reach an inflection. And what happens with the inflection is you get a point where the numbers change and the growth slows down. And then you reach an asymptote. And this asymptote might be the maximum number of people. So, if we have, I don't know what the number is, if we have like 15 billion people on Earth, the worst it could get is 15 billion people infected. So infinity doesn't make sense for modeling the COVID because we don't have infinity people. We have 15 million people or billion. So I'm just making up that number because I don't know how many people we have on Earth. But eventually then, if the infections have to change, they start growing slower. And this kind of graph is called a logistics curve. And it's a more suitable model for epidemics and things like that. And that's what Trump is trying to accomplish with the quarantining we're doing, is he's trying to control the logistics curve. And the more serious we are about the quarantining, the sooner we're going to change that that inflection point. So if we were really didn't care and we were just like living life as normal, we might have this growth go really high. But if we really work hard at containing ourselves, the logistics curve, we control the inflection point and get it to change sooner. So I think, Trump is he's leading us as a country, I think, really well to get that inflection point to happen sooner. And now I'm going to get political for a second. When Wuhan broke out, the Chinese, they saw this going on for weeks, and they would not let, they kept all their information secret and private. The World Health Organization, they did not invite them in. They did not invite any UN or any scientists to come in and explore. So what happened in China is, because they kept that information secret for like 3 weeks, it caused the outbreak to grow faster, and we didn't realize how serious it was. And that was really bad for Italy, because Italy didn't have all the data. Nobody had the correct data, so nobody knew how serious it was. And so Italy was like inviting all these people to take refuge there, but then they suffered that huge growth, and so they've got a really serious growth rate. So anyways, that's my political commentary. I'm kind of ticked off at China for keeping that secret. But anyways, so back to the math. This is a logistics curve that is what we're trying to move to. And by hopefully we'll hit that inflection point soon. Now, I'm not going to test you on logistics models. Those, if you study in the book on chapter 6, 7, there are several examples that you could learn more about logistics models if you want. In the book, there's only 3 things that I'm going to hit. I'm going to hit exponential growth and decay, and that's not going to be very much new. We've been modeling with exponential growth and decay already. We're going to hit. We're going to talk about choosing between appropriate models, and the 2 models that we have are a b to the t power and a base e to the rt power. So those are the only 2 models that we're going to be choosing between. And we've kind of talked about that too. So it won't seem a whole lot new. It'll seem more like practice. Now, this thing here, converting exponentials, it turns out we can convert ab to the t power into ae to the rt power. We can go back and forth between those 2. Normally I would talk about that too. I'm not going to make as big a deal about that. So these are the biggies. And this one is kind of lower priority. Priority, P-R-I, lower priority, if I could spell it. I'm having a spelling brain blank here. All that to say, less priority. Okay, all right, let's get going here. So anyway, I forgot to emphasize too. So Newton is going to focus you on the 3 things that I have checks here by. And the book, if you're going to study the book, don't study for the test purposes, just study the pages I have indicated, page 337 to 340, pages 345 to 545 to 547, and 547 to 548. Those are the main pages in the book to kind of help you dig deeper and understand a little bit more. Okay, so we're really just going to be practicing the stuff that we've been doing, and I'm just going to add a little detail to it, but it's not a huge detail. So we're looking at a model here. The population in Jackson was 3,800 people in the year 2007, and it's growing at an annual rate of 3.5%. When will Jacksonville's population double? So this question here, the population doubles. It is implying that we need an equation. So the only way we're going to solve that is to get an equation. So we've really got two things to do here. We've got to find the equation or the function. I'm going to say function. We've got to find the function. And then two, we have to answer the question. Okay, so now one of the things it's pretty obvious because we're studying the whole chapter of exponential growth. But in 6.8, it's not going to be obvious. They're just going to throw a bunch of numbers at us and say, which equation do we model? And so I'm going to start hinting at 6.8. Now, it doesn't tell us what the model is. So theoretically, we might have a linear model. Or theoretically, we might have an exponential model. So theoretically, it could be either one. But we have a clue here. Can anybody tell me the clue of which model to choose?
Model B.
That actually is correct. And can you give me a reason why that was a great answer? It is Model B. And can you add a little bit to like, why is that the right one?
Because it says it is growing at an annual rate of 3.5%.
Okay, so what is it about the percent that tells us Model B and not Model A?
I continue.
Just showing us the increase of how it grows. 3%, 3.5% is our growing rate, and that'd be our variable.
It's an exponential function.
Okay, you guys are all really hitting the target pretty close. I want to add something. You're conceptually getting it really strongly, but I'm going to add a little conceptual detail to this. Linear functions grow by adding. So they grow by add. So if you've got a point, you go over 1 up m. And that would be the slope, m over 1. You go over 1 up m. So we're adding m each time. And that gives us our linear function. But how do exponentials grow?
Multiplying.
They grow by multiplying. So if you have a point and you go over 1 and you go up a number, let's say it's 1.2, Well, you're going to multiply 1 times 1.2. And now you got a new number. And the next time you go over 1, you're going to multiply again. But since you're multiplying the previous number by 1.2, the multiplications get higher. So you go over 1 and you're going to multiply again. So each time you multiply, it's growing because of the multiplication, not by the adding. So that's the distinction between linear and exponentials. And whenever you see percent, what kind of math is involved with percent?
Fractions?
Say again?
Fractions?
Yes, but it's you have to take 3.5% of the population. And when you take 3.5% of the population, of is multiply. So intuitively, you guys were all hitting the target right on because you understood intuitively, yeah, oh, it's a percent. And that's because percents are of a number, which makes it a multiply. So that's going to be our model. So maybe I didn't need to talk about that because you guys were on it already. But I think it's worthwhile to have that distinction in your mind. And now that we've chosen our model is exponential, we have one more decision to make. AB to the t power or AB. Nope. The other model is AE to the RT power. Any argument? Say again? Was that a question? So how do we choose? Which one?
Second one.
What is your thinking on why to choose the second one?
Has rate. The first one doesn't has rate.
Well, actually, the first one we could use B equals 1 plus R. So we do have rate here. If we wanted to, we could use the rate. Boy, that in the first one, and of course you're right about the second one. It has a rate also. So technically, they both have a rate. So as far as rate goes, we're still free to choose either the first exponential or the second. Any other comments or input on how would we know which one to use?
Well, it would be the second one. In the word problem, it would say e to the, and since it doesn't say e to the, it would be the first one. We're talking about the annual rate of 3.5.
Okay, so you're on target with something there important. The word problem, if we're going to choose the second one, the word problem will say something. The word problem will say a very important clue if we have to use the second one. So you were right about that. Was that you, April? Yeah.
Yeah, it was.
It will say something important, but it's not going to say E. If the word problem says continuous, if the word problem uses the word continuous, then you have to use number 2. You have to use the exponential base E. Now, if the word problem does not say continuous, then you can pick either one. So in this particular problem, these are a tiny bit easier. At least for me, they're a bit easier. So if I can choose, I'm going to choose number 1. And this one does not say continuous. So this one is the one I choose. So I'm going to use a incremental growth. Do you guys have any questions about that discussion there?
Nope.
Now, theoretically, we can use either one. Now, theoretically, a biologist says, well, this one is going to be more accurate. Because that's how population is. Population doesn't stop growing. It's not like it's going to wait a year. Like there's no babies born until January 1st. And then all the babies are born on January 1st. And then we have to wait a whole more year for more babies to be born. That's not real life here. Babies are being born continuously. So the population is growing continuous. So the second model would be more accurate. But the first model is going to be close enough, and it's a little easier to use. So that's kind of my thinking here. I'm kind of giving you maybe more than I need to talk about, but I'm going to pick the first model as our model for this problem. Okay, so let's use this guy here and start writing our equation. All right, so now that we figured out, we're going to use the exponential. Population of time equals AB to the t power, and time is going to be years after 2007. And because I'm using that language for the years, for t I mean, we have a free point. At 0, which is 2007, there were 3,800 people. So that means I'm halfway done with my equation. I could finish the equation if I had b. How can we get b?
You just plug in the numbers in.
Yeah,
What,
it'd be 2007.
what numbers do I plug in for b?
Well, for A, you plug in 3,800, and for T,
That's our year, so 2007.
yeah.
So B would be our 3,800. No, not 3,800.
Yeah, b is the multiplier.
Oh, so B is 3.5.
All right, what do you guys think about that? Now we have to change that into decimal. Is b equal to 0. No, when I divide by 100,
It's 0.35, 0.035.
0.035. Let's have a discussion about that. Does everybody agree? Is that my b?
False.
I thought the would be the T because it's time. It's the annual rate.
Yeah, so time, t, is years. And 3.5% is not the years, that's the rate. So R equals 0.035. So R is the rate. It turns out the 0.35 is not B. This is a false statement.
Professor Eckert,
Yeah.
if B came out to a 1, would that be B? If that came out to 1?
So you're right about something there. This is not right, and B does involve 1. The multiplier is 1 plus R. You remember that formula from many sections back?
Yes.
Yep.
So it's going to be 1 plus 0.035. So it turns out B equals 1.035. That's the B number I can plug in. And so I can just plug that in and I have my equation all finished. Okay, now what's with the 1? Where is that coming from? Why is there 1? I just want to talk about that to remind you, because that's really important. If you forget the 1 in adding that into your B, then the whole function will be lost. And
Is it because it talks about the annual rate?
okay, can you say that again? I didn't quite get it.
Is it because it talks about the annual rate?
Okay, yeah, there's an annual rate, and the annual rate is growing based on the year before. So let's say we have 100 people in town this year, just to keep the math simple. This is year 0. Now, year 1, when we assume the population is growing, oh no, too many hundreds, never mind. Let's say it's 2,000 people. I want to keep the numbers simple. If we have 2,000 people, I'm not going to use the 3,800 just for simplicity. I'm going to use 2,000. So in year 0, I have 2,000 people. Now in year 1, we're assuming these 2,000 people are still here. So I'm assuming that population is still here and we're growing. Now we're growing by a percentage. So if we take 0.035, that's my rate, a percent, 3.5% of the 2,000, I have to multiply. And so I'm going to poke that in the calculator really quick.
And that's a BB.
It turns out to be times 2,000, I think somebody said it right, 70 people. So we've increased the population by 70 people. So what is the percent to get from this amount to this amount? What is the percent? Well, the percent is back here. Because I went from 2,000 to 2,000, that's 100%. I kept 100% of year 0. But then we increased 3.5%. So the net percent is 103.5%. Now, as a decimal, what is 100%? That equals 1. As a decimal, this is 0.035, and I'm adding these decimals, and so I get 1 plus 0.035. This is where the 1 comes from. That's why I have to have this 1 in the adding for B, because I'm keeping 100% of last year, and then I'm increasing my percent for this new year. So that was a long explanation, but I hope it helped you to reconnect and remember this formula, why it has a 1 in it. So that's where the 1 comes from. It's because we're adding 100% plus we're adding the new growth. And so that's like 100% plus the new growth rate. All right. So that was a little bit of reminder from stuff we've studied in the past. And now let's finish the model or the word problem. So something is slightly new about this word problem, but it's not a big deal. It's the word double. So now we have to answer the question. The population is supposed to double. Now, what's my equation going to be? Because I won't be able to solve anything until I get an equation.
Well, yeah, A would be 2.
Well, no, A is the start.
Oh,
So we
yeah, A
got-
is the initial, huh?
Yeah, this is our start.
I'm tripping.
Okay, so
Times
the question is when.
when.
So T is unknown. So T, I don't know. And it's supposed to double. So if it's going to double, how many people is that?
76.
16.
7,600.
Yep. 7,600, 7,600. This is the double population. So all we have to do is take the population and times by 2. And now we know the number. Oh, they're going for 7,600 people. So how do I turn this into an equation?
You make one side equal to 7,600.
Exactly. We're going to plug this in to the population. And so we plug that into our equation, and we're going to have 7600 equals 3800, 1.035 to the T power. So there we go. We created the model, and with the model, from our conversation today, I think it's important to recall B equals 1 plus R. That's going to be very important when we use the incremental exponential growth, A times B to the T power. Second thing was this new idea about doubling, but that was easy. You just times the population by 2. And now we're going to use all our algebra skills. We're going to solve this equation. So I need to get T. So this is a multiply. I'm going to divide. Now this is a division, but it's the original divided by the double, which is 2. How am I going to get T by itself?
You switch it to log form since it's actually an exponent.
Yes, this is an exponential. Now, earlier in the chapter, we didn't know how to solve this. We could not solve it. So we would graph the intersection. But now we have the algebra strategy of solving. So I can do a log to reverse the exponential. So I'm going to put a log on both sides and plug the old equation inside the log. And so now the log doesn't do anything nice to the 1.035, but it does allow me to simplify the exponent. So I'm going to be able to write log of 2 equals t times log of 1.035, and now I have t separated. T is not in an exponent anymore. T is just a regular variable in a multiply, and so we can get t by itself with dividing. So that cancels, and I'm done. I have an exact answer. I'm going to put t in front. Log of 2 over log of 1.035. Okay, so let's say that you and I are in an engineering firm and we work for the city planner of Jacksonville. And so Jacksonville's mayor comes to us and says, hey, you guys are the city planners. I want you to figure out when we're going to double. Because the mayor is thinking, if we double, we better have enough roads and enough housing. And so I want to know, how much time do I have? So if we just solved it, we can answer the mayor's question. And this is the exact answer. That is a pure, perfect, exact answer. However, if we take that answer to the mayor, is he going to be happy with it? Oh, mayor, it's going to happen in log of 2 divided by log of 1.35. Well, the mayor's going to look at us kind of crazy, like, well, I don't know what that means. Speak English. So in a physical context like this, the exact answer's not the best thing. In this case, a round off would be a lot better, because then that's what the mayor is going to understand. So now we need to pull out the calculator. Has anybody done it already? So I'm getting approximately 20.148 years. So I'm going to tell the mayor about 20 years. T is about 20 years. And so when would be the year 2027? So now the mayor knows, okay, you've got till 2027 to get the infrastructure in the city in place. But this is an example here of solving an exponential function. We modeled it and then we answered an equation. Let's go on here and look at another example. Okay. I wonder if we should do, this one's a little tricky. It's the same idea and it only has one new thought in it. I'm going to kind of introduce you to a slightly new twist on it. So a radiopharmaceutical called fluorodeoxyglucose. It decays according to this formula, Q equals Q naught times E to the negative KT power, where T equals minutes. So, question?
Did you say Q naught?
Yeah, I did. That's what this is. In physics, you'll see this a lot more. So Q is the amount.
So Q's our base.
No, Q is unknown. It's a variable. It's a changing amount. And in this case, It might be measured in micrograms or milligrams or whatever. It doesn't say, but it's the amount of the chemical. Now, in physics, you'll see this a lot. You're going to see Q naught. And they put a subscript, Q sub 0. And that always means your starting amount. So it's just a different notation for the starting number. And they call that Q naught. When we did A, B to the T power, we could say A naught is our start. So it's just different notation for the same thing that we've studied about the starting number. Does that make sense? So that is our starting number right there. Okay, one more little detail. I just think this is really fascinating about radioactive chemicals. It turns out cancer loves sugar. If you have cancer, it lives on your sugar. And so one of the things that doctors have figured out is, well, if we can make the sugar radioactive sugar, they can give you an injection of radioactive sugar. Well, the cancer is going to find that glucose. That's what glucose is. It's a form of sugar. And if they make the glucose radioactive, then the cancer is going to see that sugar. It's going to gobble up the sugar. And so when they take an X-ray of you, well, let's not say it's you. When they take an X-ray of a person who has got cancer, what's going to happen is the cancer, if it's right here, the cancer is going to suck in all that sugar. It's not going to suck in all of it, but it's going to gobble up a lot of it. So when they take the X-ray, this spot is going to glow in the X-ray because it's radioactive. It's going to have more sugar. It's going to have more of the radioactive chemical. So when they take the X-ray, they can see a glowing spot here. And that's how they can see if a person has cancer in them, because this radioactive chemical will highlight places where the cancer has been gobbling up the sugar. Okay, now imagine this. You've just been injected with a radioactive chemical. Man, that sounds crazy. I don't want radioactive chemicals in me. Well, this particular radioactive chemical, it has a decay rate. And that's why it's negative, okay? So negative means decay. And so the radioactive chemical, once it goes into your system, it's going to start decaying and metabolizing and changing into something inert. And so that's what we want. And it happens in minutes. We don't want to be radioactive for a whole year, right? So this chemical, its radioactive chemical decay happens really fast. It breaks down in a matter of minutes. So this is the backstory on this word problem that we're looking at. So they're asking us to understand the decay in this problem. All right, so in this story, we're using a different model. We're using continuous decay. Now, it doesn't say continuous, but they told us the model to use. This is the continuous model. And we don't have a choice. So they're telling us. Sometimes they don't tell us what the formula is. They say continuous, and then we know to use that formula. But they told us the formula. So I'm going to get started and figure out what is the function. So we're going to use Q equals Q naught times e to the negative KT. And we have a question here. Our question is to find K. Now, K is in the place normally when we do exponential decay that's continuous. Our function before would have been more like this. Y equals a e to the RT. And so the K number that they're asking us to find is like our R. So really we're trying to find R. So to kind of connect all the dots here, they're saying K is like the R. We got to find the rate. Now, if I were going in and they were going to do this medical procedure on me, I would want to know the decay rate. What is the rate of decay of this chemical? You know, are we talking weeks or days or minutes? I want to know the decay rate. Is it a big decay rate or a small decay rate? I'm going to want to know, and I hope it's a big decay rate because I don't want the radioactive chemical staying in me. In fact, people who have this procedure, they tell them to stay away from pregnant women for like a day or two because you're radioactive. So, anyways, I'm getting off track. I'm just really fascinated by the chemistry here. But let's get into the equation. Now, what is the starting amount of chemical that they injected into us?
Q.
Q
Q
naught.
0. So
Q naught is the start, and we don't know. Darn. They didn't tell us, are they going to put in 1 milligram, 1 milliliter, 2 micrograms? They didn't tell us. Okay, so we do not know Q naught. We do not know K. And that is the one we've got to find. This is our task. We have to find this one. Is there anything we do know? What is it? Is there anything we know for sure?
T?
Did you say T?
Yeah.
Yes.
It says 10 minutes.
In 110 minutes, we know something happens. What do we know happens? Okay, so I'm introducing you to some new vocabulary. In the last problem, the vocabulary was this word, doubling. And when it doubled, it got twice as big. Now, especially in the world of radioactive chemicals, half-life is a very important word. So, if I were to start with 60 milliliters of radioactive chemical, what's going to happen in 110 minutes?
Would it be at 30?
Exactly. If I started with 60 milliliters, then in 110 minutes, I'd be down to half. That's what they mean by half-life. The amount goes down to the half-life. So I'm going to direct your attention up to the top here and half-life. The amount is 1/2 of the starting Q naught. So half-life will be 1/2 of the starting amount. So like Jonathan said, the 60 went down to 30. Now the problem is we don't know the starting amount. The starting amount is unknown. So we can't go from a number to a number, but we can go to a formula. What is the half amount? Can somebody give me a formula?
This is the same formula they have, except for half Q.
Exactly.
Sub naught.
Yes.
Q naught. Yeah.
It's 1/2 of the Q naught. Now I don't know how much is the half amount, but I do know the formula. Okay, so which means I can plug this in. I can plug in here. I don't know how much this is, but I can plug in a formula. And I also can plug in the time. So let's see what happens. Let's take what we know and start plugging in some stuff here. So I'm going to take this Q out and plug in the formula for 1/2 the amount. Now Q naught is still the starting amount. I don't know what it is. E to the minus K. Now I don't know what K is. K is still unknown. But what about T? When I reach the 1/2 amount, how much is T?
10 minutes.
Yeah, 110 minutes. So when I plug this in, I have technically two unknowns, and I need to find K. But what would be our first algebra step to find K? Remember the last problem? What was our first algebra step to find T? We divided.
5.
Yeah, we divided both sides. Well, even though there's unknowns in this problem, that's still our first algebra step here. I have a multiply. Let's divide the starting amount, Q naught. Q naught divided by Q naught cancels. What happens over here? Q naught divided by Q naught cancels. And the net outcome is 1/2 equals E to the minus 110 times K. Let me pause for a second. Any questions? So this word problem was really exactly the same as the population problem, but they made it a little harder in that we had to start with an unknown in it. But it turned out when we divided both sides, the unknown went away anyway, so we're really down to an equation with one unknown K. Now I'm thinking, how can I solve for K? Well, this is exponential.
Log
How do
natural.
Yeah, we're going to use the natural log on both sides. And when I use the natural log here, natural log with exponential base e, it's going to give me ln of 1/2 equals, I don't have enough room here. I'm going to start that over. ln of 1/2 equals, and I'm going to take the exponent out, use the exponent law. I'm sorry, the log law. What is, oh, natural log of e is 1. These two are inverses, so they're going to undo each other anyway, so it's negative 110k. So I'm almost done. Last thing I have to do is divide. Divide, and k is by itself. K equals ln of 1/2 over negative 110. I'm going to plug that in the calculator. And I get k equals 0.0063. Now, what does this mean? What is K? I forgot. We did all this work. What does K mean?
Decay rate.
That's correct. K is the decay rate. It is the rate. Now, if I want to find the rate, I'd say it as a percent. So if we divide by 100, we're going to move it twice. So the rate equals 0.63%. So, but it is per minute. This is in minutes. So it's a decay rate in minutes. So I don't know if that's a good decay rate or not, but at least I know that at least it's decaying continuously every minute. So this is a model of half, and the other one was a model of double. This model, I think, is probably as hard as you will see them, because we had this unknown Q thing, and the continuous models aren't as natural to us. But study that one out tonight, kind of break it down, and maybe tonight redo it without looking at the notes. See if you can solve the problem again. Let's jump forward and look at another problem here. We are also at a break time, and I kind of need to take a quick break. So let's do that. Let's stop for 10 minutes. It's 10:34. So I'm going to start back at 10:44. All right, so I'll see you back here in 10 minutes.